Hello, everyone. My name is Ricardo Garcia, and I'm part of a small quantum task force at Moody Analytics. I think, as you see from the title of the talk, this is not going to be very technical, but I do have a sneak peek into the sort of use case development that we are approaching at Moody's. But I would also love to tell you about how we have designed our quantum strategy and how we envision going forward, the next years. To start off things, I would like also to clarify or at least tell you a bit more about Moody's. Most people know Moody's about their credit ratings and so on. But we also have a branch that specializes on providing financial intelligence and sophisticated analytic tools to practically every financial institution out there. So we virtually have hundreds of clients from various domains like insurance, banking, pension funds, you name it. Okay? And in there is where we see the potential to do enhancements of our products and provide the best sort of analytical tools out there with this new paradigm of computation. The agenda for the talk looks, I would start off with the hard questions. How do you convince the CEO of a firm to actually invest in quantum? I would provide what for us is a realistic outlook on how to play this long game. And then I will tell you about more concretely what are the steps and the Moody's case for playing in the quantum game as well. How do you convince your CEO? Tough question, right? You could start off saying, going back to history, right, that finance and computation have had a very unique relationship. Like, for example, Bank of America in 1955, they were already deploying the first type of computerized systems called IRMA, that they were helping you putting out the white paper and all the paper. But that probably is not enough to answer that question, right? However, the first question your CEO might ask is, before going into that, I would also like to highlight a few results from a survey that we conducted last year, and I think that these numbers, really depict the current situation on the quantum ecosystem. I will highlight a couple of these numbers. First of all, 73% of companies are yet to define a commercial advantage for quantum. What we are seeing also is that people are moving into the realm of defining business advantage, which for the financial industry makes a lot of sense. Makes a lot of sense because you need to speak that common language when you are translating, quantum volume, algorithmic qubits, which I think was kind of bunked. But these are great for system-level benchmarks, but we need to go beyond that. And business advantages can really be meaningful in finance, especially because little performance gains might be translated into a number, and that is something that can catch the eyes of senior management. But I would also like to highlight that last year, only 14% of respondents were actively investing or developing quantum capabilities, which highlights the gap on producing more research and advancing in the ecosystem. So let's back to it, answering the CEO questions. The first question that you see on my ask could be, is there quantum advantage, right? Can we find that little spot there where effectively there are no classical baselines that are competitive? We have, from the feasibility point of view, a quantum algorithm that is faster than the current best or the current baseline classic algorithm. And we essentially have an economically meaningful problem in our run. And we need to find that crosses on the intersection of these three bubbles. Well, the answer is no. Okay? The answer is definitely no. Not as yet. When will we have advantage? Nobody knows. But what I want to convey with this message that is absolutely fine, because Moody's is not a quantum company, right? We are here to play the long game, to be prepared for whatever that advantage happens, and we know that it's not going to happen overnight. But we best be prepared because we think that by being in the game, we get our early access to conduct partnerships, to establish relationships with a quantum ecosystem, and we develop those capabilities internally throughout time. It's very hard to convey. Part of my job is going out there, talking to a lot of quants, internal teams. Some of them have a background with physicists, and they do understand simple concepts like superposition, entanglement, and so on. But it's really hard for them to go deep into the mathematics of quantum and start establishing also the connections between what are the quantum algorithm options that are out there and what are they know the useful problems, but it's still that matching. There's something that needs to happen, and we need to develop those internal capabilities. Then the final answer would be: should we invest in quantum today? Yes. And I'll explain you why and how. How is the process look like? Okay. Obviously, we are not internally. I mentioned that we are a small quantum task force, so we are not actively, hiring a group or a large group of PhD researchers that are doing basic, let's say, quantum error correction. Although that might be useful in a way, but that is not our goal. We take a more pragmatic approach, hiring people a jack of all trades kind of profile that is able to speak sort of both languages, although that's definitely the hard part, right? Someone that sits right in the middle. Someone is able to translate, problems of financial modeling, which, by the way, if you go to Monte Carlo simulations, option pricing, things like that, you can get very deep into statistics and linear algebra. So there might be some connections even there. And we have seen that there are some mathematical equivalences with some of these problems between quantum mechanics and financial mathematics. There are sort of three commandments that you can take on. One is that you need to mix your domain knowledges and the processes with quantum. The other is getting to speed. It's not easy or fast. You need to train your team and start evaluating what are your key areas you want to start looking at quantum. And definitely, being a financial institution, you always have the cybersecurity angle. And our role is also to monitor the technology and inform and do the due diligence and speak to these cybersecurity teams so they can identify the crowd jewels, so they can move accordingly to the standards to getting post-quantum ready, talk to our partners that form the backbone of our network, Cloudflare, Palo Alto. What are they doing about quantum? There's obviously an angle there that we also need to take care. So, your quantum strategy, how to build a quantum team. First of all, I think Filippo mentioned this, that you really need to start, simplifying things and look at one relevant use case where you can make up for a success story and really present, how does an end-to-end quantum application look like. So at least find some, let's say, 3 relevant use cases that show potential promise. But it's more than that, right? There's a whole lot of things you need to take care, right? One thing I would like to highlight is that there's a lot of people are coming out to us and say, can you demo us to a quantum computer? How can we access a quantum computer? And there's definitely ways, right? But what I mean is that don't just, tell, just show. Build something practical, even if it's oversimplifying. There's something like a Python application that, it's optimizing portfolio, and show it. Because quants, a lot of the quant job is to do model iteration, model development, and they're continuously testing and validating their problems. So it's essential that they have this sort of routine as well in the quantum world. Be realistic. Don't fall into the hype. And have a frugal approach to things, right? Just for funding. And again, it's also one thing is very key is identifying your internal champions. So these are people from different areas that have the expertise, the domain knowledge on the financial modeling problems, and that they will support you throughout this journey. These are the key people because they are also the ones that keep the energy going and through this long process. And I'm just going to mention this, that by doing this, we're seeing a lot of cross-pollination side effects in a way. We are getting together a lot of people from different backgrounds and across, and we're seeing that one of the side effects is that we are getting inspired to approach problems in a novel way, but just putting people of different backgrounds in the same room. One aspect that is also key is that when you are translating these concepts, you must talk in a quite generic or simple language, right? So translate complex problems into simple words. Start from there, even if it sounds that it's not very meaningful to you. Start from there, and then slowly turn that into the actual financial industry applications that we're looking at. So at Moody's, as I mentioned, we are a global risk assessment firm. So we decode risk across a whole range of native domains. So that means cyber, climate, macro, supply chains kind of risks, geopolitical kind of risk, right? So we take a look at risk from various angles. One area we're also interested in is how does quantum affect climate modeling. There are certain ways that there might be a possibility through quantum-enhanced machine learning protocols, and how, because they are very computational, a lot of computational challenges. Or it might just be solve these partial differential equations that provides us with an informed view of risk if we are able to solve that. Okay? On the other hand, we also have the typical use cases you might find in risk management. We also run Monte Carlo simulations. A lot of the times, when we end up, especially with this view of risk, we end up with a huge number of risk factors and also a huge number of time steps, especially depending on your horizon. And this huge space of state variables make the problem very challenging, that you need to adhere to numerical approximations, such as numerical integration, Monte Carlo kind of workflows. So definitely an interest to speed those up, because they will sort of reduce a lot the electricity or the cloud bill in a way, right? We also have use cases on reinsurance, like reinsurance portfolio optimization and dynamic asset liability optimization, which are particular hard instances that go beyond the Markowitz-style kind of portfolio optimization. And we think that these are the areas where the hardness of the classical solvers, only classical heuristics remain competitive. But if you go beyond thousands of variables, things start getting interesting for maybe a new paradigm of computation. The Moody's case. So we are focused on 4 pillars. One is obviously the security and defense angle, where we're trying to both adhere to quantum. We have the angle of product enhancements, so actually looking at the different use cases and areas where we can identify potential improvements in time to solution or accuracy. And we also keen to partner with people from the quantum ecosystem to develop use cases jointly. We also have a thought leadership pillar, where we also try to act as leaders of thought in terms of talking to our customers and describing to them what the quantum technologies ecosystem looks like today, and develop those together with our key clients as well. And we also are actively in the community, engaging with the community. So we have been to the MIT Quantum Hackathon. This year, we've attended also last year the ATH Hackathon, providing the challenges that look more like the end user kind of applications. And we try to foster that community as well by sponsoring and co-organizing hackathons and other local quantum communities. So let's take it now a kind of semi-deep dive into what use cases we're actively looking at. One of the goals of Moody's is coming up with a sort of tailored solution to have an integrated view of the risk analytics, right? So we will start from, here in the left, from generating what are called systematic risk scenarios. Systemic risk scenarios, essentially mean kind of macro and climate factors that affect the whole globe in a way. And these are really the anchor points from where we generate different scenarios. So think about scenario analysis, stress testing. These represent our kind of anchor points from where we generate then probabilistic views through the stochastic scenario expansion module. So we now generate a probabilistic view across different forecasting horizons of all these macro and climate horizons. Additionally, we also overlay what I'll call idiosyncratic shocks. So these are particular shocks, points in time, through these distributions of the different factors that you see here, as you see here on the bottom, that have a particular effect on that simulated path. So this can be, this Russian event of supply chains that affects your portfolio in a way, or some kind of, cyber attack also affecting, the distribution of your assets, right? Once we have overlaid all these different factors, and you start seeing that we are quite now in a high-dimensional space now, right? We need to come up with a common measure of the asset value distribution, which is we are interested. So imagine we have a portfolio of assets, which can be financial instruments and or things like loans, commercial real estate, or things like that. Now we have a distribution of the assets, and that represents our common measure, where we now can start, translating things into shareholders in terms of risk and reward views. I didn't mention, but one example of idiosyncratic shocks as well, it can be, the hurricane risk that affects Florida as well. We're taking that into account as well. So we have this holistic view of risk, across many, many domains. And finally, you can come up with, integrated risk metrics, which also model the interdependencies between among all these different risk factors. So our key question was, where across the whole pipeline can we identify where quantum computation can be meaningful or have promise to, speed up things or improve the quality of the scenarios that we are generating, and so on. Oops. So last year, we kicked off a series of different use cases. One that I will also mention later on is this asset liability optimization problem that we are particularly interested in, because we think that from the classical perspective, it's quite hard. Once you go into different, we start adding different complexities, and I will talk this about briefly. So we are interested on achieving, or applying different quantum solvers and trying to see that even little performance gains could be meaningful there. Another problem is, generating better idiosyncratic shocks. So that is trying to forecast the intensity of tropical cyclones much better, in order to inform better the generation of synthetic storms that then would conform, a view on the hurricane risk. Okay, there are a few observations of hurricane tracks or tropical cyclones, so we usually take a scenario generation approach to those problems. And having better intensity models would be really meaningful, because we are lacking that accuracy today. Not in track, not for hurricanes track. That's a point to make there. Another problem we have also in the climate modeling space is we have these hydrodynamical models that are very useful for flood risk analysis that are based on a kind of nonlinear partial differential equations. So we started wandering into that realm of trying to apply quantum algorithms to solve this kind of nonlinear PDEs. We have some problems as well. Quantum mechanics is naturally a linear framework. So it's definitely, I think there's much work to do on the research side of things to try to accomplish, meaningful algorithms for nonlinear PDEs. We also looked at things like Bayesian inference, closely related to Monte Carlo simulations. But in this problem, we take a Bayesian view to some of our core models in some of the climate and econometrics applications, and we have very high processing times, especially when the dimensionality is big. And here, we started looking at different approaches, because we also think as quantum computers as this kind of probabilistic hardware accelerators that could be meaningful to speed up Bayesian inference problems. And we are still actively researching on that side. And finally, a work we did with Ricardo. We ask a very simple question that we provide as a service to clients in the form of risk recession prediction. What is the probability of a recession happening during the next 12 months in the US, for which we have plenty of data. And we were trying to see if we could apply methods from what are called signatures that are quite useful for the quant toolbox. And we tried to see if we could lift those signature features through quantum embeddings, utilizing techniques like signature kernels and so on, and to see if we could improve the current baselines that we are applying classically. So that's a bit of our view on the different use cases. But we are also looking at, as I mentioned, simulation problems. Solving high-dimensional integrals will be something very interesting for us because we have a lot of these use cases end up with, especially on the pricing side of things, end up, can we solve this high-dimensional integral through various methods? And in here we're looking at quantum-inspired approaches and quantum computing approaches such as the amplitude estimation as well, and how can we squeeze out as much performance as we can with the current quantum subroutines, utilizing different kinds of quantum middleware as well. Finally, I just wanted to maybe motivate why are we especially looking into this instance of portfolio optimization. So the general problem looks very much like your classic statistical asset allocation problem. But especially there are two directions that you can sort of not artificially increase the hardness of the problem, but essentially you could adopt a dynamic rebalancing strategy. So that means that you're adding sort of that extra dimension, time dimension to your problem, saying that now instead of just doing a single period or a static optimization where I have my expected returns, my covariance matrix, and I apply the optimization, I have to do that maybe sequentially or find the optimal trajectory along many periods of time. That becomes computationally very hard. Another way to increase the hardness, and this is because we actually want to this is some of the assumptions of this problem need to be broken down, is that we could include alternative freeze measures. So variance lies on an assumption that is not useful for industry, and we are more geared towards risk measures of the sort of value risk, conditional value risk, and especially if pension funds, for example, are interested on value risk measures. And that makes the problem also very computationally hard, especially because it becomes a mixed integer kind of problem, for which would be interesting if we have quantum solvers in that realm. And let me just go over briefly over this. We also partner with Multiverse to develop a platform that tries to eliminate those high barriers, especially in the domain of product integration. Reduce integration and preparation time. How can we effectively provide to these quants a platform where they can iteratively, test and validate these different solvers, being quantum-inspired quantum solvers, and make their journey much, much easier, and put them metrics that they actually understand, business metrics that they actually understand, and they don't have to, talk about quantum volume, this is my circuit depth, and so on. And again, we also, with this product, with this platform, there comes from a problem marketplace, a set of problems that are quite generic, but still can lift you up and start.
I'm sorry, Ricardo, but we'll have to wrap up.
Okay.
We're over time.
Okay, that's fine. Yep. So let me. Yes. Yeah. Thank you.